partition of a sample space. Partition of a sample space. A set of events E1, E2, etc. En is said to represent a partition of the sample space S if it satisfies the following conditions. First condition, Ei intersection Ej equal to null set where I not equal to j, ij 1 to up to n, and E1 union E2 union etc. union En equal to sample space S, and probability of Ei is greater than 0 for all I equal to 1 to etc. n. So if the events E1, E2 etc. En satisfy these conditions, it is called partition of the sample space S. So the first condition is Ei intersection Ej equal to null set. If I not equal to j, if I equal to j, what happens? Ei intersection Ei, both are same events. So Ei intersection Ei, that is Ei itself, not null set. So when I not equal to j, Ei intersection Ej equal to null set. This also, or in other ways we can say they are disjoint, pairwise disjoint. Disjoint means they have no common elements. If you take any two events, they have no common elements. That is the meaning of disjoint sets or events. So here Ei intersection Ej equal to null set, that means pairwise disjoint. Pairwise disjoint. And E1 union E2 union etc. union En equal to S. That means the union of these events E1 etc. En, union, their union is equal to sample space. That property is called the events E1, E2 etc. En are exhaustive events. They are exhaustive events. Exhaustive events. And one more condition, probability of Ei is greater than 0 for all I equal to 1 to etc. n. That means we know always probability lies between 0 and 1, including 0 and 1. Here it should not be 0, it should be greater than 0. Probability of every event Ei, that means E1, E2 etc. en, anyone, if you take any one event, its probability should be greater than 0. So these are the three conditions to be satisfied for this to be a partition of the sample space. So it is very important term, partition of a sample space. So a set of events E1, E2 etc. En, they are called partition of the sample space if they are pairwise disjoint. First condition, they are pairwise disjoint. That means if you take any two events, their intersection is null set. They have no common elements. Second, they are exhaustive events. Exhaustive events means their union equal to sample space. Third, they have non-zero probability. Should be greater than 0. Probability should be greater than 0. So if these three conditions are satisfied, so we can say E1, E2 etc. En form a partition of the sample space if they are pairwise disjoint, exhaustive, and they have non-zero probabilities. That is the condition. These are the conditions for the events E1, E2 etc. En to be a partition of the sample space S. So understand that term, partition of a sample space. Next, theorem of total probability. Theorem of total probability. That is also very important theorem. Using that we can study Bayes theorem. Very important theorem, Bayes theorem. Theorem of total probability. That is, if E1, E2 etc. En is a partition of the sample space. That means if it satisfies these three conditions. So if E1, E2 etc. En is a partition of the sample space S, then, and also A is any event associated with the sample space S. So related to that experiment, A is any event. In that case, we can say P of A, probability of A equal to probability of E1 into probability of A given E1 plus P of E2 into probability of A given E2 plus etc. Last, probability of En into probability of A given En. And in other way, we can write that using sigma, we can write sigma that is equal to sigma j equal to 1 to n. P of Ej, probability of Ej into probability of A given Ej. So using sigma we can write like this. So that is the theorem of total probability. Theorem of total probability. That means if E1, E2 etc. En is a partition of the sample space, that means they satisfy the conditions. They are pairwise disjoint, they are exhaustive, and they have non-zero probabilities. Then, and also A is any event associated with that random experiment or associated with the sample space, yes, then probability of A, probability of that event A is equal to probability of E1 into probability of A given E1 plus probability of E2 into probability of A given E2 plus etc. probability of En into probability of A given En. Or using sigma, that is equal to sigma j equal to 1 to n probability of Ej into probability of A given Ej. And I will explain to you one example of partition of a sample space. Consider the experiment of throwing a die, throwing one die. So what is sample space S? S equal to 1, 2, 3, etc. 6. So in the experiment of throwing a die, the sample space is 1, 2, 3, 4, 5, 6. Then consider the two events. Consider the two events A equal to set 1, 2, 3. And B is the event 4, 5, 6. So consider the events A and B in the experiment of throwing a die. Sample space is 1, 2, 3, 4, 5, 6. And let A be the event 1, 2, 3. B be the event 4, 5, 6. Then here A and B form partition of sample space. Partition of sample space S. Because their union, what is their union? A union B, that is equal to S. 1, 2, 3, 4, 5, 6. So they are exhaustive events. Then A intersection B, they have no common element. So A intersection B is null set. So that condition, so A intersection B null set, that condition satisfied. A union B equal to sample space S. Then their probability is greater than 0. What is the probability of A? That is 3 by 6. That is 1 by 2. Probability of B, 3 by 6, 1 by 2. That is greater than 0. So all these three conditions are satisfied. Therefore, A and B form a partition of the sample space S. So that is one example for partition of the sample space. So that is the so understand these two terms. Is very important term, partition of a sample space, and understand the theorem of total probability. Okay.